Jesus. Oh, we're live. Okay, so hopefully this will be there so you can see it later, right? If not, we'll try it again and I'll do it better next time, right? Nah, I'm just going to use this for now. Should be all right. All right, let's go super simple. First and foremost, what do we need to know to be able to solve a related rates problem? What's the first thing I need to know? I need to know implicit differentiation. I need to differentiate in terms of something else, right? We were able to start small. We were able to go ahead and take that y equals 3x cubed minus 6x and differentiate that, right? In terms of x. And that's really what we were doing. We were using Leibniz to ddx it, and we would say, oh, well, this differentiation is 9x squared minus 6, right? And that's how we started. Well, now we had to move on because all functions in life don't necessarily have just one variable in them. They're not just these linear or parabola functions, those quadratics or our cubic functions, which make the S. Now we have functions that have multiple variables. And we need to differentiate, yes, but in terms of a specific variable. And I think where we got off the rails was not only did we take an equation that we already know, a formula that we already know, but we differentiated for something completely different because we were looking at physics and we were looking at motion in terms of time when there was no t in the function itself. There was no t in the formula. And so everything had a dA dt, dV dt. And it was like, I threw you into a tailspin. So I want to go back and go slow. And everything like these Pythagorean theorem problems are probably the easiest to work with. Right? So we have a ladder. It's a 20-foot ladder, and it's leaning against a building. And if the bottom of the ladder slides away at a rate of 2 feet a second, how fast is the ladder sliding down the building when the top is 12 feet above the ground? Right? So they're giving you some information. And being able to access and put this information together is probably the most difficult part. Right? We know, super simple, ladder's 20 feet long.
Yeah, 20 feet long.
20 feet long. Right? We know now that we're taking a snapshot in time. We're not watching the whole thing fall. We're not watching the whole progression of the ladder sliding down this wall, right? Because this is the wall. And this is where it's 12 feet off the wall, right? This is 12 feet up here. And now we can make a right triangle out of it. And the cool thing about this is a 3, 4, 5 right triangle, right? So we already know that this is 16. But we don't have to know, do we?
Being so smart. Let's go simple.
We don't have to know that, do we? We don't, because we know that Pythagoras said that, and I'm going to give these different letters instead of A, B, and C. Is that all right? I want to call this, because it's vertical, I'm going to call this Y. Because this is horizontal, I'm going to call this X. And I'm not a big fan of S. I'm going to call this Z. Okay, we're going to call hypotenuse Z from now on. It helps us in physics and calculus to use those ideas. Oh, I'm on. Okay. Just don't turn the sound on or it'll drive me nuts. So we're moving on. We have this idea. We can figure out what x is just by using Pythagoras. And we're going to say that 20 squared is equal to 12 squared plus x squared. And now we do the math, right? X squared, 400 minus 144, 256. Did I get that right? 400 minus 144 is 256. I think I did. Seems reasonable. 256. What's the square root of 256? Look at that. It works out perfectly. Didn't we say earlier that it had to be 16 because of the 3, 4, 5 right triangle idea? Okay. And there it is. We did all our math, right? I didn't show you this. Didn't show you this.
So now we know the value of all.
Did that make sense? Did I go too fast? Cool, cool. I just knew that this was 400 and I knew that this was 144. So I just subtracted. Cool?
Yeah.
Potts, you good?
Yeah.
You're already good with this stuff. This one's okay. Now I know my lengths. Now I can start to do some other stuff. Now I'm going to take that same formula, the Pythagorean theorem, x squared plus y squared equals z squared. And the worst thing about this is, what have we been given? Some number of feet outward along the x-axis over time. There's no time here. So now I have to differentiate this whole thing. I'm going to use a different color so we know that we're doing something different now. I'm going to flip it around in a second. We're going to dt. We're going to differentiate all of this stuff in terms of time. And while it looks like it's the worst thing ever made, I'm going to rewrite it like this. d dt z squared equals x squared plus y squared.
Would you have to differentiate the z squared?
I'm about to. I'm going to show it right now. Thank you. I just wanted to write it in it. I wanted to turn it around. Make it forward facing. This is the Hebrew version, the right to left version. This is the English version. Do we read Ukrainian left to right? Yeah. Cool. So now we'll differentiate. And this is where we got mad before. I'm going to write it over here because I'm running out of space. Let's go ahead and take the derivative of z squared. We have 2z, right? Right? But I need to show that I differentiated
2z, dz, dt.
dz dt. I differentiated z. That's what this dz means. This is z differentiated in terms of time. So every time I differentiate a different variable that doesn't have a t, I need to put that variable differentiated in terms of
It's
time.
going to be equal, and then the same thing with the other one, which is going to be
2x
dx, dt.
dx dt and 2y dy dt. So I've differentiated every variable in terms of time. That's what it says. That's what this means in respect to, in terms of And what it really means is how fast is it moving in the z direction per second? How fast is it moving in the x direction per second? How fast is it moving in the y direction per second? Well, we're given one of those pieces of information, aren't we?
Yeah,
We're given
the rate.
we're given the horizontal direction, and it's moving
Dx.
to the right. That's our dx dt.
So you
We've been
substitute.
given dx dt of 2 feet a second. Cool?
Because it's going to the right and x is
Now.
horizontal.
What else do we know? We know that the length of the ladder, unless it's an expandable ladder, ain't gonna change. So we know that dz dt, the change in length of the ladder in respect to time, is nothing. It won't change. So this is really cool. We have all of this information that we can use and then move on with.
Why do we know dz dt is 0?
Because the length of the ladder never changes. It's not an expandable ladder or a contractible ladder. So
And dx
the length
dt
of the hypotenuse will never change.
Okay.
The sides, the legs of the triangle are going to change because this is going to expand 2 feet every second. This is going to come down to just a little
If
less
it
than
said
that.
something like with the, I don't know, with the ladder expanding at a rate of 1 meter per second.
Yeah.
Then our dz dt will be 1 meter.
Well,
per second.
remember, we're going to have a boat problem where the line that's bringing the boat into shore is your hypotenuse. And as they roll that line
It will
in,
be constantly changing.
that changes. But what doesn't change? The height from the water up to where that crank is, right? So there's going to be one piece of this puzzle that doesn't change.
The next step will be plugging the values into our formula.
Plug our stinking values in. Now, can we do one more thing to make our lives easier? What is when we look at this,
The two.
they all have a 2 in. Now, I'm going to rewrite this whole thing over here since I have space, and I don't have limited amount of space on my video here because I didn't put it way back there. I'm going to rewrite z
C stays.
dz
That one stays.
dt. I'm just rewriting the whole thing.
Everything, yeah, that's what I was.
X dx dt plus y dy dt, and now I can plug everything in that I have.
Do you keep the z variable when you're replacing it? So we know dz dt
Yeah.
is
Yeah, because I know that z is 20 feet.
So it's gonna be 0 equals dx dt is.
Is it okay if I write everything there? Is it all right if I write everything?
Yeah.
I don't want to lose a single soul on this. So I have 20 feet. And my dz dt is 0. So I'm going to multiply by 0 meters a second. And that's going to be equal to x. Well, x is, whoops, 16 feet. 16 feet times, and this is important because it's going to give me a chance to use my units. What's dx dt? It's moving at 2 meters, feet per second. I don't know why they use feet so much in calculus class when we're talking about physics. It drives me crazy.
They're like feet.
Threw it away.
I like feet. I like feet. I like feet.
Oh, there we go.
They're all like feet.
I guess I should have shut that off anyways. Anyway, God, that's messy, isn't it?
Do
Oh,
we
my-
know what is dy dt?
What is dy dt? That's what we're solving for.
Oh, so we just leave it like that so we can
So we have 12 feet dy dt. And that's what we're going to solve for. Cool?
Where, so it's gonna be 20.
So doing math, we've got 0 equals 32
Plus 12.
feet squared per second plus 12 feet dy dt. I'm going to subtract my 32. Didn't I get 32? Subtract 32 from both sides. Minus 32 square feet a second. This is going to go away pretty soon, but I want to show it to you. Because in physics, units are super important. All right? I ran out of space. I'm going to divide by 12 feet. Sorry about running out of space. Now, this is the cool thing. This is the physics piece of the puzzle. This feet cancels out with one of those feet. So we're still going to have feet per second when we're done, which is exactly the unit type of unit we're looking for. This goes completely away. So our answer is dy, the change in height per second is going to be, what is that, negative 8/3? Negative 8/3 feet per second. Isn't that 32 over 12?
Yeah, that is.
It was a long way, right? It's a long way to go just to get to that one spot. Is that all right?
I have a struggle with something. When we get the problem, I struggle to like know how it is. Like the shape and if it's a cylinder, I struggle with that. Is there something in advisor?
Cool. So let's do, if you turn it over, I think the first problem on the back of the page is a cylinder. I'm almost positive that they're drilling a hole, right?
Yeah.
They're drilling a well, because that's, every physics problem in the book. So we have this on camera. We'll be all right with this. I hope this works out. I may start doing this regularly. I may just set it up back there and hit the live button and record every darn thing I do in here, because it might keep kids from doing something silly. All right, so our problem is this. It says an oil company is drilling a well. The drill creates a cylindrical well with a radius of 4 feet. So I'm gonna write that down first. The radius is 4 feet. That's the first piece of information they give me. If the depth of the well is increased 12 feet an hour, now we're talking about some rate of change. So I'm going to assume the depth is dH dt, and it's 12 feet per hour.
And you thought it was a.
And I can make this depth, because I'm talking in terms of physics. I get to decide whether up is positive and down is negative, right? I get to decide on my own. It's subjective, it's physics. So I'm going to keep that as positive. Is that all right?
Yeah.
How fast is the volume changing? How fast is the volume of this well increasing if it goes down 12 feet an hour? And so what are we looking for? dV dt, right? Where how much is the volume changing in that same amount of time? Cool? Now we need to know. What's the formula for the volume of a cylinder?
Is it 1/4?
2 pi radius, 2 pi radius.
That is surface area.
No, but it has a 1/2 on it. It has a 1/2.
Relax.
It's 1/4.
Volume equals pi r squared h. Isn't that what it is?
I don't know.
Please say yes.
Yeah.
Yeah.
Calculus.
I mean, Google it. I don't know. I seem to remember this is pi r squared h, right?
It's so hard, sir. I'll Google it.
Cool. Cool. So when I different, well, yeah. When I differentiate this, when I go ahead and I hit the button and say, hey, dV dt this, or ddt this, there we go. This is going to be the first part of my differentiated formula.
And how do you do it like pi? You do dr dt?
Well, watch, we can leave pi as pi. It's just a coefficient, right?
No,
So
I mean about
v, let's differentiate v, and all we're left with is dv dt. Right? Now, this is where the fun starts, right? This is where the fun starts. It's a little bit difficult. I have, yeah. All right. Let's leave our pi. We have a problem, right? We have the product rule.
Yeah, we have to change R and H and.
We can, we can. but we don't have to, but we can, right? I can go ahead and rewrite this as a sum, right? Right? I can say this is F and this is G. Let's just go ahead and try it this way for fun. It's annoying, and Javi's gonna get mad at me for doing it.
I don't understand. So if you explain like another way of doing it, I will never.
So-
do that.
This is a product, right?
Mhm.
So this is the first part of my product. This is the second part of my product. So this is, we count this as function F and function G. And so I say 2 R dr dt times H, right? Plus, and then take the derivative dH dt times r squared, right? Cool? It's annoying. It still exists. It's a lot of work. It looks funky. But we have these answers. We do. We have a lot of this in here. And it's going to be really cool. We do have our height that changes. And this whole thing right here, this piece right here is going to disappear.
Yeah.
Do you know why?
It's just the way.
Do you know why? Because the radius doesn't change. It's the same drill that's going straight down into the ground. So the radius isn't going to change. So really and truly, this is all I'm going to deal with here. This is going to disappear. And I forgot I have to.
Ow.
Are we gonna solve for it? Is
Yeah.
that the next
Cool.
step?
Okay, so now let's start plugging stuff in. I'm looking for DVDT. I have my radius of 4 feet. So that's 4 feet squared, which is 16 square feet, times my DHDT, which is 12 feet per hour. Look at that. That's awesome. Just multiply. And don't forget pi. That coefficient has to get distributed because I have a sum. I have my sums. Does that make sense? When I pull it out, I have to distribute my pi to both sides. Do you see that? Okay. So this is one of these things where I have to distribute to both pieces of the sum. Okay. So I stick a pi here, and we'll be good. dv dt. I don't know what 12 times 16 is off the top of my head. Ah!
Why 12? Oh, we're,
192.
and what's up with the age?
What age?
That age.
This?
Yeah.
Doesn't matter. Why doesn't it matter? Because this right here is
the radius
0.
never changed.
Because
Yeah.
this never changes. The radius doesn't change over time. So this whole piece right here goes away,
How do we know DRDT is 0?
right? How do we know DRDT?
Do you keep the pi though, or you don't? You
Yes. I just said we distribute the pi to both parts of that sum.
Originally, like how it used to be, it would be like dVdt.
So
equals-
you see this piece right here? This is like if we had pi out here and this was x minus 2. This piece right here is the x, and this piece right here is the minus 2. We would be distributing pi to both. Or I'll make it plus because it looks better. Right? They're both the same idea. Okay, what did I say? 196? 192. So when feet squared is
feet cubed.
feet cubed per hour, and then I have 192 pi. Look at that.
So
I have my cubic feet per hour, which is volume to time. All right.
192 pi or 192?
192 pi feet cubic feet per hour.
Why is the pi in the middle?
You want to put the pi up front?
Like I would have liked like 192 feet and then the pi up.
No. That looks better, doesn't it? Straight up downtown. Oh, that's my. That's me showing my age. Paula Abdul. You guys don't even know who that is.
I do.
Do you?
Musician. Yeah.
All right. It's a long way to get there, right?
Fuck. It's on YouTube.
Sorry.
So make sure to share this to everyone.
You rotten child. Now, what we were trying to figure out is there going to be a cool way to relate, and this is what Bibli was trying to get me to. Is there a cool way to relate my height, right, to my radius? Because I really haven't been given a height, I can't.
If you would have been giving a
If it said tell me what the volume is at this height. I could have related
Even
my
though,
height to my radius.
so even if it would have had.
Did
a
you hear
height-
it?
No, we were trying to hear you.
Go ahead. Go
Even
ahead.
if you had a height, it would have been still been zero, right? Because it would be the RDT still zero.
Right, I just wanted to show you that sometimes, and we hate it, right? We despise the idea of having to, now we'll really be able to hear it, really having to use the rules again, the product rule. Oy vey, the mirror. Now we gotta use that stupid thing again. But they do rear their ugly heads. When it comes to cones, the cone problem that you're gonna see next, we do get a chance to relate our radius to our height. There was one, was it this one? Yeah, number 3. You just multiply by 8. But I'll explain it later. Any other questions before I shut this bad boy down?
So there's a video online and there's live.
Yeah,
Yeah.
I'll clip the.
Anything else I can do for you
No, that'd
to
be
try and make your life easier?